pandas, NumPy, scikit-learn, TensorFlow, and PyTorch, which are used in the training of models, in the training and deployment of models, and each have different uses. Then we have R, which is mostly used in advanced statistics and academic research use cases, and SQL, which is essential for querying relational databases. Then lastly, we have Julia and Scala, which are used for high performance computing and mostly for big data processing. And yeah, together these languages and libraries are used for data processing and analysis. Then next we have the platforms and infrastructure. So first, we have the cloud, AWS, Azure, Google Cloud, which are used for compute and managed services. And second, we also have the data stores where the data is stored. That's Postgre, MongoDB, Snowflake, Databricks, depending on the use case. And also for processing, we have Apache Spark or PySpark for large-scale distributed compute as an example, but there are others. And also for the writing of the code, we have Jupyter. They're used primarily of notebooks such as Jupyter, Google Colab, and DeepNote, which allow you to code and also have markdown text to explain or to break down your findings or your analysis. So next we have the ETL or orchestration, which ETL stands for extract, transform, load data pipeline. And for this, we use Apache Airflow or Power Query, which are automated pipelines or workflows, and which also do schema management. And then for machine learning and AI, which is an extension of data science, we use scikit-learn for classical machine learning, TensorFlow or PyTorch for deep learning, and H2O or AutoML to automate the manual and repetitive tasks of the machine learning pipeline. And yeah, lastly, we also have the platforms like Hugging Face, where you have access to pre-trained, cutting-edge large language models. And lastly, we also have visualization and BI tools. The most common being Matplotlib or Seaborn or Plotly for programmatic charts, and then the more commercial tools like Tableau or Microsoft BI for executive dashboards and interactive storytelling.
So the next is about why data science matters in information system management. So data science benefits organizations by helping them move from reactive to proactive decision making. By proactive, I mean organizations are able to anticipate future outcomes and then make informed decisions based on the data. So the first way that it does this is that through predictive and prescriptive analytics. So in predictive analytics, you're able to forecast demand. For example, if it's demand for a product, and then through prescriptive analytics, you're able to get informed recommendations, like for example, how much stock you need to buy to be able to accommodate such a specific season. The next is advanced cybersecurity. Um, Nowadays, cybersecurity is a bit enhanced by data science through um, analyzing patterns, especially for threat detection. Um, and then there's business IT alignment, which quantifies IT value and guides investments so systems support high impact business activities. And then the last one is through enhanced decision making. As I had said earlier, organizations are able to do proactive decision making thanks to insights from the data.
I'll be taking you through the risks, limitations, and governance challenges facing data science. So the first point is operation and technical risks. Data quality failures such as the garbage in, garbage out, model drift and algorithmic bias can produce erroneous or unfair outcomes. Continuous monitoring and validation are essential. So, garbage in, garbage out is where if the underlying data is noisy, biased, or incomplete, the analytical models can produce like flawed insights, which can lead to like poor strategic decisions. Model drift is where, since data science models are dynamic, the changes in environmental conditions can cause shift in like market trends or consumer behavior, and which may cause the model to reduce in quality over time. And the next one is algorithmic bias, and this is common, and this is where like there's a human or societal biases in the models, which can lead to like unfair outcomes. An example can be in the interviews. Yeah. The second one is structural and financial risks, high costs for talent, compute, and maintenance. The black box opacity of complex models can hinder auditability and trust in regulated contexts. So the first point, right, says high costs for talent. There can be high costs for talent, like an example can be the data scientists and engineers, the cost of their salary, which can be like extremely high. Yeah. The second point, which is the black box opacity. This is where like highly complex models such as deep learning or neural networks, they can lack transparency, and it can be hard to explain why a model made a certain decision. Yes. So the third point is governance and regulation. Regulatory frameworks such as GDPR and Kenya Data Protection Act demand privacy-preserving design, data minimization, and clear consent, plus policies for data sovereignty and breach response. Uh, Kenya Data Protection, oh, sorry, the GDPR is a European Union Act that demands a right to uh, privacy. So, yes, I'm done.
Next, we have the ethical considerations, and ethics must be embedded across the life cycle from responsible data collection to transparent model use and accountable operationalization. The following are the considerations. These considerations protect individuals, uphold trust, and ensure legal compliance. We have informed consent, where data is collected with a clear purpose and it's obtained with consent where required, and provide users control over their data usage and deletion. Fairness and bias audits regularly test models across demographic groups, implement bias mitigation, and document trade-offs and limitation to ensure there's no bias in your models. We have transparency and explainability, provide stakeholders with understandable rationales for automated decisions, and maintain logs and explanations for audits. Data quality and provenance, track lineage and transformation to ensure traceability and reproducibility of analysis and model outputs.
Real-world applications in healthcare. We have predictive patient risk and diagnosis support, where we use historical health data to identify high-risk patients early and support clinical decisions. We have resource optimization, where we analyze patient flow and demand patterns to improve scheduling, bed allocation, and equipment use. We have EHR analytics, where we extract insights from digital patient records to improve treatment quality and operational efficiency. And we have disease surveillance, where we track population health data and detect outbreaks and support public health planning. Next, we have marketing and CRM systems. Here we do customer segmentation and targeting, where we group customers based on behavior and preferences to support focused marketing strategies. We have personalized recommendations, where we use data patterns to suggest products or services tailored to individual users. We have campaign performance analytics, where we measure marketing results in real time to optimize strategy and budget allocation. And finally, we have customer lifetime value prediction, where we enhance long-term profitability of customers to guide retention strategies. Next, we have finance and banking, where data science helps with fraud detection and anomaly monitoring. Here, we identify unusual transaction patterns to prevent financial losses and security breaches. We also have credit scoring, where we analyze the financial history and behavior to evaluate loan eligibility and risk levels. We have financial forecasting, where we use historical data to predict revenue costs and market trends. We have algorithmic trading insights, where we apply predictive models to support automated investment decisions. Now, finally, in marketing and supply chain, we have predictive maintenance for equipment, where data science, where we use sensors and performance data to measure failures before breakdowns occur. We have demand forecasting and inventory optimization, where we predict product demand to reduce shortages and excess inventory. We have production process analytics, where we monitor production data to improve efficiency and reduce waste. And finally, we have quality control and monitoring, where we detect defects and process deviations in real time. So the key takeaway is across industries, data science enhances information systems by enabling intelligent automation, predictive insights, and strategic decision support. Yeah, thank you.
I'll take you through the conclusion and the key takeaways. The first one is that data science helps information systems management plan ahead and not just react. So basically, data sciences change how organizations work. Instead of just looking at past results, it helps them predict what will happen and make things run better. This turns information systems management into a powerful tool that uses predictions to manage resources, prevent system problems, and offer personalized experiences to users. And then good tools and clear steps are essential. For data science to succeed in information systems management, you need reliable tools and ways of working that can be easily repeated. This involves using programming languages, flexible cloud platforms, and machine learning operations that are tools to manage AI models. And then having clear documented steps and keeping track of changes is crucial. This ensures that solutions can grow, are easy to maintain, can be checked, and are dependable. It also helps teams work together and avoid confusing and unexplained processes. And third is ethics and rules, the ethical considerations. When data science is used in information systems management, it's vital to have strong rules and ethical guidelines. Protecting personal data, making sure AI decisions are fair, understanding how models make decisions, and following regulations are all key to building trust. Ignoring this can lead to a bad reputation, legal trouble, and people losing faith in the system. And the final recommendations are to truly benefit from data science in information systems management. Companies should bring together diverse teams of data scientists, industry experts, and IT professionals. They need to set up ongoing checks and rules, and like tracking how well performed models perform and doing regular audits to ensure everything stays ethical. It's also important to make AI choices clear and easy to understand, encouraging a culture where everyone trusts and uses data-driven decisions at all levels. This complete approach ensures data science brings real value and a lasting advantage. Yeah, thank you. And that has been group 4. So thank you.
Thank you very much, Group 4. I think I don't have time for you. There is a gentleman here who is coming for something. You come with your group after class. Hello. Thank you very much. I think when we talk about data science, you guys you have to mark. This is the way the world is going. And I explained to you, I think in class, one of the physical classes, the very first class, the importance and the steps of being a data scientist. It doesn't just require computer science. You need to have very good knowledge in business. So this, as time goes, things dictate. Right now, if you even do a course like BCom or CPA, it will help you a lot, or any other qualification that is business. Beside that, the mathematical thinking, your knowledge on mathematics is also very important in data science. And it's all about dealing with data and analyzing data and visualizing. I think the presenters have very well highlighted what it is, the way it works for business, and benefits and all that, and what it is involved. You can enrich further, and it's not something that you can forget. You must put it in weight as the in thing. Our time, or 5 years ago, 3 years ago, they used to talk about data analytics. 5 years ago, they used to talk about big data. Some time back, it was not there. So, ladies and gentlemen, is an opportunity. Next group.
We're next. Group 5 is next. Let me share my screen.
Just share.
Can everyone see my screen?
Yeah, it has to be entire screen so that you can share as a slideshow.
Okay, okay. Is that better?
You guys are not responding for this, gentleman.
Is that better? Can everyone see?
Yes, we can see.
Okay, okay. So we are group 5, and our presentation will be about AI application systems. So we'll be talking about how intelligent systems are reshaping industries and everyday life. So for the introduction part, AI application systems integrate artificial intelligence technologies into practical use cases, enhancing decision-making and automation across industries. These systems leverage data, algorithms, and computational power to deliver intelligent solutions that improve efficiency and innovation. Understanding their scope and components is essential for maximizing their impact in today's digital landscape. So the first segment of our presentation will be on AI application systems overview. So definition and scope. What are AI application systems? AI application systems are software platforms that use artificial intelligence to automate tasks, analyze data, and support complex decision processes. Their scope spans multiple industries, including healthcare, finance, and manufacturing, providing adaptive and data-driven solutions that evolve with changing inputs and environments. So the next part, I'll hand it over to Sophie to proceed. Sophie,
Hello.
yeah, we can hear you. We can hear you.
I'll be presenting the key components of AI application systems. So let's start with data collection and data sources. AI systems rely on large volumes of relevant data from sources such as databases, sensors, user input, or logs. The quality, diversity, and accuracy of this data directly determines how effective the AI system will be. Data processing. Raw data is unorganized and usually useless as is. This component handles data cleaning, normalization, labeling, and transformation so the data is suitable for training AI models. Poor preprocessing leads to unreliable outcomes. AI models and algorithms. This the brain. It includes machine learning, deep learning, or rule-based algorithms that learn patterns from data and make predictions or decisions. The choice of model affects accuracy and speed. Training and validation. In this phase, the AI model is trained using prepared data and evaluated using validation and test datasets. This ensures the model learns correctly and generalizes well to now unseen data instead of just memorizing patterns. Computing infrastructure. AI systems require adequate hardware platforms such as CPUs, GPUs, cloud services, or edge devices. This infrastructure supports model training, deployment, and real-time inference. Deployment and integration. The trained model is deployed into real-world applications and integrated with existing systems, such as web apps, mobile apps, or enterprise platforms. Monitoring and maintenance. After deployment, system performance is continuously monitored to detect errors by bias, drift, or degradation. Models are updated or retained as data requirements change. Security, ethics, and governance. This component ensures data protection, system security, ethical use, compliance with regulations, and responsible decision making. It includes access control, auditing, and transparency measures. I give it to Felix to do benefits and challenges.
I'm going to take you through benefits and challenges of AI applications. I'm going to start with benefits. Can you all hear me?
Yes, we can. We can hear you.
Okay. So the first benefit, automation that actually saves time. AI handles repetitive or redundant tasks that can easily be too much for humans. Data entry, log analysis, customer support, both threat detection. Number two, faster and better decision making. AI goes through massive datasets in seconds and spots patterns humans miss in cybersecurity, finance, healthcare. This means smarter decisions with no guessing and more evidence. The third one, improved accuracy. Machines don't get tired, emotional, or lazy. Trained well, AI reduces human error in things like diagnostics, fraud detection, and image recognition. Another benefit, scalability. Once deployed, AI systems can serve millions of users at the same time. No payroll, no burnout. Personalization at scale. Recommended recommendation systems, adaptive learning platforms, targeted security responses, AI tailors experiences to users. The last one, 24/7 availability. AI doesn't sleep. Systems keep running, monitoring, responding, and flagging issues of the Yeah, I finished it. Challenges of the AI application systems. The first challenge, data dependency and data quality issues. Garbage in, garbage out. If the training data is biased, outdated, or wrong, the AI will definitely be wrong at scale. Second one, high development and maintenance costs. Building AI systems isn't cheap. You need resources like data, computer power, skilled people, and ongoing updates. The third challenge, ethical and bias concerns. AI models learn from historic and real world data, which may contain existing human biases, discrimination, or inaccuracies. When such data is used, AI systems can unintentionally produce unfair or discriminatory outcomes at scale, affecting decisions in areas like hiring, healthcare, finance, and security. The fourth challenge, lack of transparency. Many AI models make decisions that even their creators can't fully explain. That's fun until you need accountability in law, medicine, or security. Security risks. AI systems can be attacked, poisoned with bad data, or exploited. In cybersecurity, attackers now use AI to it's an arms race with fewer rules. The last challenge of AI applications, job displacement fears. Some roles will disappear or shrink. New ones appear, but the transition is messy and people don't love being told to just reskill. I'm going to hand to the rest presenter, Dwayne.
The next presenter, I hope you guys can hear me. I'll be taking you through the healthcare and medical applications. So, as you all know, AI will transform healthcare by making diagnosis faster and more precise. So we are also hoping for AI to take healthcare to the next step. As I start off with number one, medical diagnosis and imaging. Healthcare will be AI systems will be used to analyze X-rays, MRI, and CT scans in the lab slides. What it does, it identifies patterns too subtle for the human eye and flags high-risk cases for doctors to review. So this speeds up diagnosis. Number two, predictive analytics. This can be used. These doctors can use patient data to predict healthcare risks in the future. This helps forecast conditions like heart diseases and diabetes. Examples predicting heart diseases, yeah, and early warning systems for sepsis. Yeah. Number three, personalized treatment. AI can be used to analyze genetic data, lifestyle factors, and past treatment outcomes to recommend tailored treatments. This Yeah, pardon, sorry guys. AI can be used to analyze genetic data, lifestyle factors, and past treatment outcomes to recommend tailored treatments. The applications are customized cancer therapy, drug selection and dosage optimization, and also chronic disease management. Number four, virtual health assistants. AI-powered systems interact with patients for basic care. These users are symptoms checking, appointment scheduling, medical reminders, and answering common medical questions. You guys, I hope you have interacted with the chatbots. They offer these services. Number five, drug discovery and development. AI, due to the use and help of AI, it speeds up the process of discovering and testing out new drugs. This reduces research times and costs. How? By identifying promising drug compounds. It simulates drug interactions and reduces time and cost of clinical trials. Number 6, robotic surgery and clinical assistance. AI, the use of AI assists in surgical planning and precision. These examples for these clinical procedures are surgical robots guided by AI, real-time feedback during procedures, which reduce human error in delicate operations. Thank you. I'll hand it over to the next presenter, finance and business applications.
Hello, thank you very
Um,
much. Yes, yes,
uh,
go ahead.
so I'm going to take you through the finance and business application. So we'll start off with fraud
Sean, just be
detection.
on video.
Pardon?
Be on video when you're presenting.
Okay. So first, I'll take you through fraud detection and prevention. So AI systems monitor transactions in real time to detect unusual or suspicious behavior. So how do they do it? Number one, they identify abnormal spending patterns. Number two, they flag potential fraud instantly. And number three, they reduce false positives compared to rule-based systems. Uh, the next one is process automation and operational efficiency. AI automates internal business processes. How is it applied? So number one is invoice processing. We have payroll automation, supply chain optimization, and contact analysis. Uh, so number three, we have financial forecasting and business intelligence. AI supports strategic decision making by analyzing historical and real-time data. Examples, you have revenue and expense forecasting, budget optimization, and performance analytics. The other one is credit scoring and risk assessment. AI analyzes financial history, transaction behavior, and alternative data to assess creditworthiness. How is it applied? You have loan approval decisions, interest rate determination, default risk prediction, and yeah, number five, we have algorithmic trading and investment analysis. So AI systems process market data, news, and trends to support or automate trading decisions. It is used in high frequency trading, portfolio optimization, and market trend prediction. So autonomous. Let me also take you through autonomous systems and robotics. So for we have autonomous vehicles, which act as mobility as a service. So this involves self-driving cars, trucks, shuttles, and delivery bots that navigate without human input. AI processes data from cameras, lidar, and radar to perceive the environment, for example, in marking traffic signs and pedestrians. It then makes real-time decisions on steering, braking, and routing to safely transport people or goods from point A to point B. For example, you have the Tesla full self-driving mode, which is available in most of the Tesla models. Number two, you have industrial manufacturing, which involves smart factories. Traditional heavy machinery is evolving into intelligent collaborative robots, which are known as cobots. AI enables these robots to perform complex tasks like assembly, welding, and quality inspection. Computer vision spots microscopic defects on a production line, while machine learning allows robots to adapt to slight variations in parts, making assembly lines more flexible. For example, we have the robotic arms assembly electronics, AI-powered visual inspection systems for car paint quality, cobots working alongside humans on assembly lines. Number three, we have domestic service robots. So consumer-grade robots use AI to handle household chores with increasing intelligence. They utilize simultaneous localization and mapping to build a map of the home, then identify obstacles, for example, like carpet waste or charging cables, and optimize cleaning patterns. They can even recognize specific objects and adapt their behavior based on the room type. For example, we have robot vacuums. So, number four, we have healthcare and assistive robotics. AI enhances robots in medical settings with varying levels of autonomy. Number one, we have, for example, surgical. In surgical, AI analyzes pre-op data to guide robotic arms, enabling surgeons to perform complex procedures with superhuman precision and minimal invasiveness. Number two, we have rehabilitation. So intelligent exoskeletons and therapy bots adapt to a patient's movement, providing customized assistance during recovery. Then you have hospital logistics. So autonomous carts deliver linens, meals, and medication, freeing up staff to for direct patient care. An example we have is the Da Vinci surgical system, which involves and wearable robotic suits for mobility impairment and also delivery robots in hospitals. Next one, we have warehouse and logistic automation. In massive distribution centers, AI coordinates fleets of robots to handle inventory. These systems are computer vision to identify These systems use computer visions to identify specific items and path planning algorithms to navigate crowded floors efficiently. They optimize the supply chain by automating the picking and placing of goods, significantly speeding up order fulfillment. For example, we have Amazon Robotics drive units moving entire shelving pods, autonomous forklifts in manufacturing plants, and sorting robots in postal services. Next, we have AI in cybersecurity. AI will start with AI acting as a defender. So the cybersecurity landscape is an arms race, and AI is a critical asset on both sides. So this is what it does. Number one, we have threat detection and response. AI analyzes AI analyzes network traffic, user behavior, and system logs in real time to identify anomalies that signal a breach, often before it causes damage. B, we have vulnerability management. AI scans code bases to identify potential security flaws and predict which vulnerabilities are most likely to be exploited. C, we have combating AI powered attacks. Attackers use AI to create more convincing phishing emails and evolve malware. Defensive AI must adapt just as quickly to recognize these new sophisticated threats. D, we have automated incident response. So what happens is upon detecting a threat, AI can automatically isolate affected systems, block malicious IPs, and initiate containment procedures by human experts precious time. Precious time. Okay, I'll give it to the next person. Okay, I'm Alex. I'll be presenting AI models and algorithms. So, types of AI learning. AI models aren't one size fits all. So this means there are multiple uh, AI models. They learn in different ways depending on the task and available data. There's the first one, supervised learning. The model learns from labeled data, e.g., thousands of pictures labeled cat or dog. Use case, it's used to detect spam messages in emails and messages. The second one is unsupervised learning. The model finds hidden patterns in unlabeled data. It's used in customer segmentation, grouping users by purchasing behavior without predefined groups. So, and also anomaly detection. The third one, reinforcement learning. An agent learns to make decisions by interacting with an environment to achieve a goal, receive rewards or penalties. It's used in training robots, game playing, like nowadays you see AI, in FIFA and whatever. Uh, Optimizing traffic, light control. The fourth one, generative AI, a subset of deep learning that can create new original content. Text, images, code, audio, based on the patterns it learned. Use case is writing emails, creating marketing images, generating synthetic data for training. Uh, Generative AI in action. The new wave of content creation, generative AI, is not just another algorithm. It's a new paradigm for human-computer interaction. Uh, the first one, text generation, drafting emails, reports, and code, powering advanced chatbot and customer service, summarizing long documents. The second one, image and video creation, generating market assets and product mockups from text description, and enhancing video quality or creating special effects. The third one, code generation, assisting developers by suggesting code snippets and auto-completing functions. Uh, Good example of this is the Visual Studio, translating code from one programming language to another. The fourth one, synthetic data, creating realistic but artificial data sets to train other AI models, especially useful when real data is scarce or private. I'll give it to the next presenter, Brad.
I'm Bradley. I'll be taking you through the human AI partnership augmenta- augmentation, not replacement. Shifting the focus from automation to collaboration, the most powerful outcomes arise when humans and AI work together, combining their unique strengths. Some of the AI strengths are speed and scale, pattern recognition in big data, consistency and endurance, and handling repetitive tasks, while the human strengths are creativity and intuition, critical thinking and strategic context, and empathy and ethical judgment. Therefore, AI handles the how, freeing humans to focus on the why and the what if. So this leads to augmented intelligence using AI to enhance human capabilities and not replacing them. So key takeaways and looking ahead. The road ahead for AI systems. AI is a foundational technology. The way electricity or the internet is, AI is becoming a ubiquitous part of the technological landscape, transforming every industry it touches. Success is a journey, not a destination. Implementing AI is not just a one-time project. It requires commitment to continuous learning, monitoring, and adaptation. Responsibility number three: responsibility is non-negotiable. The long-term value of AI depends on building systems that are fair, transparent, secure, and aligned with human values. Number four, the focus is shifting. The conversation is moving from can we build it to how can we build it responsibly and how can it best work with us. I'll give this to Nate.
Okay, so for the conclusion bit, you can say AI application systems transform industries through intelligent automation and data-driven insights. While benefits are substantial, success implementation requires overcoming challenges related to ethics, costs, and expertise. Embracing AI strategically fosters innovation, efficiency, and competitive advantage in the digital era. And that is the end of our presentation. Yeah, that's the end.
Okay, Abba. Hello, thank you very much. You people, you've done some good work. I really like that presentation and a bit of the generative AI. How many of you have had an experience of use of generative AI? Let's start with the group members.
I have.
In which way? Generating code?
Yes, yeah, I've interacted with the agents, the AI agents in Visual Studio Code or Android Studio.
Wow, that's good. Another person, please, in the class, away from code generation and agents. So, ladies and gentlemen, fundamentally, you notice you have to have primary knowledge first of everything so that AI can help you. You know, AI comes in as an addition. It starts from what you already know, and it cannot help someone who doesn't have an idea on one particular field. So this is the high time to learn so many things, and now use the power of AI to actually compound, to increase, to improve that knowledge. Thank you very much. Please share that presentation or all the presentations with your in your WhatsApp group. Let's have the next group.
Group 6, we're presenting on robotics. Let me share my screen. Can you hear me? Hello.
Yeah, I can hear you.
Okay, so group 6, it should be group 6. We're doing on robotics. These are the members. So we start. Let me share my camera. I forgot. So robotics group 6. So we start with what is a robot. A robot is typically defined as an automated machine that can be programmed to carry out certain activities either with or without human assistance. So robotics basically is the interdisciplinary science and engineering of designing, building and operating machines capable of performing tasks autonomously or semi-autonomously. Unlike traditional machines, robots are distinguished by their adaptability, precision, and ability to interact intelligently with humans and surroundings. So we have sensors that help enable robots to react and adapt to changing conditions. The core characteristics of robots include sense, which is perception of surrounding through sensors, then decision making through algorithms, and physical movement through actuators. Actuators are like components of a machine responsible for moving and controlling systems that help to convert energy into mechanical motion. So these are some examples of robots. We have camera, a millimeter wave radar, and the likes. And then we have robots versus traditional machines. In adaptability, unlike fixed function machines, robots react to environmental changes using real-time sensor feedback loop. And then in programmability, robots can be returned for entirely different activities through software updates. So like robots can be programmed through different languages like Python, that when they are programmed, they are programmed to do certain commands. And then there's interaction. Advanced robots use AI to recognize human presence, voices, and even emotion for safe collaboration. And from here we go to the historical background of robots. In ancient Greece, we had a mythical creation called Talos, which represented early human imagination about machines that could act autonomously. So the Greek people had this thing in mind that maybe one day we could have something that could act on its own and do tasks, do everything. Then we have Ismail Jazari in 1206, who pioneered the camshaft automation. In his book, The Book of Knowledge in Ingenious Mechanical Devices, he described various mechanical devices like a musical automation and an elaborate hand washing machine. Here, his robots used gears and levers to automate tasks, laying groundwork for future robotics. And then in 1921, Karel Capek's play, where he popularized the term robot. And then the rise of robotics I think this was the first industrial robot. It was called Unimate, which was the first industrial robot. It was installed at General Motors, revolutionizing manufacturing, and this was done by two great scientists, Engelberger and George Devol. And then Asimov, he, he created three laws of robotics. That was Asimov in the mid 20th century. These laws were: a robot may not injure a human being, or through inaction allow a human being to come to harm. The second one was: a robot must obey orders given to it by human beings, except where such orders will come to conflict with the first law. And then the last one was: a robot must protect its own existence, as long as such protection does not conflict with the first or second laws. I'd like to call upon the second person to continue.
Hi everyone, good morning. I hope you're all doing well. I'll be taking you through the classifications of robotics. As my predecessor has just talked about industrial robots, I'll be diving into the other classifications of the robots other than industrial. So beginning with industrial themselves, industrial robots, they they tend to be like workhorses used in industries. Mostly they automate the tasks that human beings do, as we see in in automobile industries, the way robots are used to create cars. So a good example would be having stationary arms focused on speed and 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 doing dangerous tasks. Then we have service robots. So service robots are designed for human-centric tasks like surgery, cleaning, or warehouse delivery. In this current era of the year, we've seen so much of surgeries being done by robots to ensure precision when doing very sensitive surgeries. And we've also seen sensitive tasks like cleaning of windows on big buildings being automated by robots. So that's a task that's done by service robots. Then we have humanoid robots. Now, about a year ago, or maybe 3 ago, we heard of Sophia. It was a robot that was brought about from the Western world to interact human abilities, and it falls under the category of humanoid robots. So it mimics the human body to interact with environments that are built for humans, and it can tend to do other tasks such as assistance at home, which it can work as a nanny, it can work as very many things. Okay, you can go to the next slide. Okay, on to the mobility and the autonomy levels. I'll be taking you through the mobile robots. So mobile robots navigate using LiDAR, GPS, and cameras. As my predecessor has also said, that robots use sensors to detect the environments and to make their decisions using the data collected from them. We've seen this LiDAR, GPS, and cameras which they use. And also we have the cobots, which I had someone in another presentation talking about. So they are collaborative robots designed with safety sensors so that they can work directly next to humans. Then we have autonomous robots. This is something that's so common to us in this current era. We've heard of the autonomous vehicles that are being developed, such as Tesla, the Cybertrucks that are mostly dominant in the Western world. And we've also heard of the rovers. The rovers are mostly used in space exploration. For example, in Mars, when they are doing as an exploration, we had the rovers working as robots to gather intelligence and information of how the environment in Mars looks like. That's it for my presentation. I call upon the next presenter.
Hello everyone. Next, we have the components of a robotic system, which is the hardware architecture. So a robotic system is not just a single machine. We have a complex integration of several core components that work together to enable perception, decision-making, movement, and task execution. First, we have the mechanical structure. Think of this as the robot skeleton. It includes the physical frame, links, joints, and the chassis. Its primary job is to provide the necessary support, shape, and rigidity while defining the robot's degrees of freedom for movement. Next, we have the actuators, which these ones functions as the robot's muscles. These components produce motion by converting energy, which is usually electrical, into mechanical force. Common examples of the actuators we have DC motors or hydraulic cylinders. The other components that we have are the end effectors. This is the hand, or a specialized tool located at the end of a limb that directly interacts with the environment. And depending on the robot's purpose, this can be the grippers, suction cups, or even the welding tools. Those are the end defectors. Next, we look at the electronic and sensing core of a robot. For a robot to understand its world, it needs sensors. These are the sensors that gather data about the robot's internal state and the external environment. We use tools like cameras and encoders to be able to get the feedback, perception, and safe operation that is using the sensors. We also have the control system, where we say that every robot, as we know, needs a brain, which we call a control system. Usually, this is a microcontroller or a computer, and this system processes all that of the sensor data that we get. It runs algorithms and sends out the final commands to the actuators. Finally, we have the power system. None of this can work without a power system. This is the energy source such as the batteries for mobile units or AC/DC supplies for fixed robots. This also includes the regulators to ensure every component that it receives has a stable voltage. I'll pass on to the next person that will be presenting.
So next we have the ROS, which is basically a robot operating system. A robot operating system is like an open source software framework used to develop robot applications. An ROS is a flexible middleware providing libraries and tools to help software developers create robot applications. The components include we have nodes, drivers, community, and a large community which has libraries for navigation and vision. So the drivers include the hardware agnostic interfaces, and the nodes are independent processes communicating through messages. And then we have the logic and control strategy, kinematics, which is a mathematical modeling of motion without considering forces, mapping joint angles to tool positions. We have PID control, which is the standard feedback loop that corrects errors between a target actual position in real time. And finally, the path planning, which is an algorithm that finds the safest and most efficient route through a complex 3D environment. So examples of ROS can be used in making autonomous vehicles, research robots, drones, service robots. We have many universities and research labs use ROS because it simplifies robot development. Digital twins and simulation. We have Gazebo and Webots, which is a high fidelity physics engine which allows developers to test code in virtual space before physical deployment. This is safe, for it ensures no risk, for there is no risk of crashing, and then there is efficiency. Then it is cheaper to iterate designs virtually because it is free. And then we have the next presenter can present.
Good morning. I'll be talking about AI and machine learning in robotics. Artificial intelligence, or AI, in robotics refers to the integration of intelligent algorithms that allow robots to perceive, learn, reason, and make decisions independently. Uh, Unlike the traditional robots that only follow pre-programmed instructions, AI-powered robots can adapt to new environments, improve their performance over time, and respond intelligently to changing conditions. Therefore, in simple terms, AI acts as the brain of a robotic system. It processes information collected from sensors and transforms that data into meaningful actions that the robot can perform. So, there are three major learning approaches that are used in robotics. The first one is supervised learning. It's from the previous slide. In this approach, the robot learns from labeled examples in order to perform classification or prediction tasks. E.g., for the financial institutions and credit card companies, they use supervised learning models to identify potentially fraudulent transactions by analyzing the patterns and anomalies in transactional data. The second approach is unsupervised learning. The robot analyzes unlabeled data and identifies hidden patterns or relationships. A common example you can say is the music recommendation systems, which analyzes listening habits and user preferences in order to suggest songs or create personalized playlists. The third approach is the reinforcement learning. In this method, the robot learns through trial and error, receiving rewards for correct actions and penalties for incorrect ones. And you can say a well-known example is the robotic hand, which was developed by OpenAI, which learned to solve a Rubik's Cube, and it took 4 minutes on average after learning from repeated attempts. Another important technique related to machine learning is the deep learning. Deep learning uses artificial neural networks with multiple layers, which greatly improves a robot's ability to interpret complex data such as images, speech, and audio signals. Let's move to perception and decision making. We start with computer vision. Computer vision allows robots to interpret and understand visual information captured through cameras and sensors. Through the computer vision, robots can detect objects, recognize faces, estimate distances, and navigate through environments. The process usually follows some steps. The first one is that the robot captures an image using a camera or sensor. And next, the system processes the image to extract important features. And then it analyzes patterns in the data and finally makes decisions based on the interpretation. Computer vision plays a critical role in applications such as the autonomous navigation, industrial quality inspection, medical robotics, and object manipulation. E.g., for an AI-based computer vision system, it can detect and count vehicles in real time by using image recognition and object tracking algorithms. Another important concept in robotics is autonomous decision making. Autonomous decision making refers to a robot's ability to analyze information, evaluate possible actions, and choose the best response without human intervention. This process also typically follows a decision making cycle. First, the robot senses the environment through sensors. It then interprets the collected data using AI models. Thirdly, it plans the possible actions based on the situation. And then it selects the best decision. And finally, it executes the action and evaluates the outcome. Several AI techniques support this process, including neural networks, probabilistic reasoning, path planning algorithms, and behavior trees. Uh, because of these technologies, autonomous robots equipped with advanced sensors, cameras, actuators, and AI systems are now capable of performing tasks and making decisions independent without the constant human supervision. So, with that, now I'll hand over to the next presenter.
So I will be taking you through industry and healthcare. In industries, robots are used to perform repetitive tasks such as automotive welding, assembly, and warehouse logistics. AMRs, which are autonomous mobile robots. They are also used in the medical sector to perform minimal invasive surgical systems such as Da Vinci and robotic prosthetics for rehabilitation in the form of autonomous tractors and precision harvesting drones. They are also used in exploration and defense to explore deep frontiers, which are places where humans would otherwise have trouble exploring or accessing. So, NASA has rovers that explore the Martian surface, and AUVs map the ocean floor, which are environments that are lethal to humans. They're also used for defense and security. UAVs for surveillance and bomb disposal robots prevent human casualties in active threat zones. I'll be passing on to the next presenter.
Okay, my name is Mohamed. I'm thinking through robotics and information system management integration. As usual, robots must align the organizational information system to drive strategic business value. The key integration points are the ERP systems to obtain real-time production data feeds, cloud analyst performance and health monitoring, First of all, information system management refers to the management of technology systems that collect, process, store, and distribute information. It includes databases, software systems, networks, data analytics tools. It helps organizations manage information effectively to support operational decision making. Integration of robotics in ISM, robots become part of a larger intelligence system. The robots collect data from the environment and send it to information system for processing and analysis. Examples include factories, where robots communicate with management systems to optimize production. Healthcare robots that send patient data to hospital information system. Warehouse robots connected to inventory management system. The key benefits of robots and information integration: increased efficiency. Robots automate repetitive tasks, reducing time, increasing productivity. Better data management. ISM collects and analyzes data generated by robots. It improves accuracy. Automations reduce human errors. Real-time monitoring monitors can monitor robotic operations through information systems. It also reduces cost over time, automation labor, and operational cost. In conclusion, integrating robotics with information system management allow organizations to combine automation with intelligent data management. This leads to smarter operations, improved productivity, and better decision making. As technology continues to evolve, this integration will play an important role in the future industries. Thank you. With that, I will pass to the next presenter.
So I'll go through the human dimensions one by one and become one. So this the human dimension will all fall under challenges, ethics, and future trends of robotics. So job transformation, robots replace yes.
Just be on,
Yes.
video, be on video. Just be on
Okay.
video and then, yeah, there's some echo sound, but it's okay. Just be on video.
Okay. So job transformation. Robots replace multiple repetitive labor that create high-skilled technical managerial roles. The challenge with this is managing the transition and scaling the workforce. Open the next slide. Okay. So the challenges are subdivided into four categories, where we have economic, technical, ethical, and social. And economic, we have high initial capex, where the impact is difficult for SMEs to adopt. In technical, we have application difficulty, where struggling is harsh and unstructured areas. And in technical challenges as well, I can argue how we have unstructured environments that are mentioned in the input. We have energy efficiency, where the battery limitation, continuous operation takes, sorry, just a minute. Okay. Energy efficiency. Battery limitation constraints operation takes time for mobile robots. Power computing for AI further reduces endurance. Still, under technical challenges, we can also have sensor reliability, where sensors fail in robots, decay or provide lazy data. Robot systems need redundancy and fault tolerance. We also have identity processing, which is a challenge as AI algorithms demand significant power to compute. Balancing sophistication with redundancy requiring this is challenging. We also have manipulation dexterity, where human level dexterity remains elusive. Handling defining new objects, slippery surfaces, and delicate items is difficult for robots, something which humans can easily achieve. We can go on to economic values are explained a bit more. Apart from the difficulty for SMEs to adopt, we can also have high initial investments, where industrial robots typically even cost between 85,000 to over 400,000 US dollars. So integrating tools in infrastructure adds a significant expense. We also have ROI uncertainty, where small and medium businesses struggle to justify costs networks, web applications. This is because the limits are typically able to be adopted by large companies, but small enterprises cannot justify the cost of owning them. Let's have maintenance costs. Although maintenance software, updates, and technical support requirements is expensive and scaling, where there is a shortage of robotics engineers, technicians, and integrators during production. Some mitigation strategies of the economic and technical, we can have robots as a service, RaaS, where it supports subscription models, reducing the upfront costs. We can also have improved development tools, which lower technical barriers. We also have standardization, which helps in reducing integration complexity, where businesses will now be able to integrate robotics into their daily operations more easily. We have education programs, which help in making robotics workforce, many system, which is scalable solution for them SMEs. Next, I'll pass on to the next presenter.
We have finished. That was the last present. That was the last present. Thank you for your attention.
Well, thank you very much. I think you've done some good, very good work, you guys. DeepSeek and all that kind of thing. And what goes to the robotics? There is a very nice, fascinating video I always like uh, showing people. There's one called Sophia video in YouTube. It's an AI and very many other sophisticated robots that have actually been invented. And I like the way you went into what exactly makes a robot work that intelligent. So you good work, guys, Regan and the group.
Yes.
Let's now have the next group because of time.
Okay.
Next
Before,
group is
before there are some people who are telling me that they have been locked out. They are here to present, and the meeting is full. Hello. Next person can go.
Good morning, everyone. My name is Nicole, and my group and I will be taking you through knowledge systems.
Nicole.
Yes.
Sorry, just before you go on, as you share your presentation, let me create another link, and you guys can just and I will share. I'll share another one. Nicole, just go on, and then I can communicate.
I hope all of you can see my screen.
No, I can't see your screen clearly.
Oh, do I share now like the entire screen? How do I share it?
Kindly zoom a bit.
Can you see it clearly now?
Yes.
Okay. I hope everyone can see my screen. My name is Nicole Namai, and my group and I will be taking you through knowledge systems. So, what are knowledge systems? A knowledge system is a computer program that utilizes a centralized repository of expert facts and rules combined with a reasoning mechanism to simulate human problem solving and expertise within a specific domain. So, knowledge systems process data and use rules to generate new knowledge and decisions. So an example of a knowledge system is a sales system, which takes in data. Data is raw facts. For example, in a sales system, an example of data is 100 units are sold, and the information that it gets from that is information is data with context, and the information that it gets from this data is that sales are down 10% this month. So the knowledge that this system will give us is sales are down because a competitor launched a promotion and we should counter with a loyalty discount. So not only does it help you with new knowledge, it also helps you to make a new decision. Now, for example, if you are a sales company, you guys are able to counter the other company, which is your competitor, by offering a loyalty discount to your customers. So core functions of our knowledge systems are knowledge acquisition, that is, a knowledge system gathers knowledge from external sources or internal experts. For example, it conducts data mining or documenting lesson learned after a project. Another core function is knowledge storage, where it uses structured databases, cloud repositories, or knowledge bases like a corporate wiki to keep information searchable and organized. A corporate wiki is like Wikipedia, how if you want to search for a celebrity or whatever it is that you want to search for, you'll always find it in Wikipedia. Another core function is knowledge dissemination, where it ensures the right person gets the right info at the right time through push notifications, search engines, or training portals. Another core function is knowledge application, where it uses the knowledge that it has gotten from the facts and the data that it has been given to solve problems, make decisions, or improve businesses. So again, back to the example that you are looking at, this one for the sales system, it has helped us with this new knowledge that you've gotten. I'd like to give to the next presenter, Muri, to continue.
Hello. In this section, I will explain the core architecture of knowledge-based systems. A knowledge-based system is designed to imitate how human experts make decisions, with an important feature in that it separates knowledge from the processing logic. This makes it easier to update and maintain. Firstly, knowledge knowledge-based system can be separated into three important components. First is the knowledge-based, which is considered the heart of the system, as it stores facts and heuristics. Facts are the true statements about the domain, and heuristics are expert rules or guidelines, which are often written in an if-else rules or if-then rules. Secondly is the inference engine, which is like the brain. It processes the information in the knowledge base and uses logic reasoning to reach to conclusions. It commonly uses techniques like forward chaining, which starts from known facts, or backward chaining, which starts from possible conclusions and check if the fact supports it. And thirdly, there is user interface, which allows users to interact with the systems. Nicole, are you still presenting? Give me a
I
moment.
think, Brian, you can just present.
Can everyone still see?
Yes.
Yes.
Okay, so as I was saying, thirdly is the user interface. It allows users to interact with the system. Through the interface, users can enter information, ask questions, receive recommendations or results from the system. And it's also designed in a way that also non-experts like students or organization members can use it easily. Another key component, even though it's not listed as the top three, is called the explanation facility. It's a unique component that allows the system to explain how and why it reached a specific conclusion. Now, when you look at it like that, you can also say that AI is the same as knowledge based, but it's not, because knowledge based systems use structured human rules and domain specific knowledge to solve problems, whereas artificial intelligence often utilizes data driven machine learning algorithms to discover patterns and make predictions. The key benefits of everything that I've just mentioned is it's debugging and making updates, since it makes it easier for knowledge engineers to update and debug rules. Transparency, which improves users' trust by making the system's reasoning visible rather than a black box. And decision support, which provides better support to professionals by showing the underlying logic behind a recommendation. And with that, I'll take it to the next person, Lisa.
Good morning. My name is Lisa, and I'm going to be taking you through the knowledge engineering process. Can you hear me?
I think you are not observing. Put video. Be on video always.
Okay. Okay. So I'm going to be taking you through the knowledge engineering process, which is knowledge engineering is the technical process of computing, organizing, and encoding human enterprise into a structured, machine readable format. The goal of this is to translate unstructured tactic knowledge into explicit automated reasoning system. So the roles in knowledge engineering, there are two. We have a knowledge engineer and a domain expert. So the knowledge engineer acts as a translator and an interviewer who interviews the domain expert, a human who is a human specialist with years of experience in a specific field, could be a doctor, could be a lawyer. The task of an knowledge engineer is to extract knowledge from the expert, organize it, and choose the right programming logic to encode it into the system. The task of a domain expert is to provide the facts, intuition, and rules of thumb that the system will use. The focus of a knowledge engineer is for structure and methodology, and the domain expert provides context and wisdom. Next slide, please. Move. Okay, so the knowledge acquisition, The core objective, the goal of knowledge acquisition is to convert an expert's intuitive and structured knowledge into an explicit structured format for the knowledge base. That is, the key tools are the knowledge acquisition programs and efficiency. The knowledge acquisition programs specialized software is used to provide an organized interface that allows experts to rule to enter rules or cases directly. Efficiency, these programs automate certain steps to reduce the manual labor of the knowledge engineer. Next slide, please. The
I'm
process
there.
flow. The process flow. So we have the first process is planning and scoping, which involves defining the boundaries of the problem. That is the action being done is defining the boundaries of the problem. Then the goal is to identify the specific domain, the goals of the system, and the available experts. Those are the domain experts. Acquisition, which is the action being done here, is gathering information, and the goal is to interview experts and extract the facts, rules, and logic needed for the system. Conceptualization and structuring, the action here is organizing raw data. The goal is to determine the relationship between different pieces of knowledge and how they fit together. The initial phases define the system's IQ and domain depth. The next process is the next slide.
I'm already there. Can you see?
No, not on my side. Okay. I can see it now. The next process is formalization and implementation. The action being done here is coding the knowledge into a format that the interface engine can understand. The goal is transforming the conceptual relationships into actual rules, logic gates, or cases structures within the software. And then the last process is testing and refinement. The action being done here is validating the system against the expert judgment. And the goal is to identify errors in reasoning, refining rules, and ensuring the system's output is as accurate as the human professions. Thank you. The next presenter.
Hi, so I'll be taking you through the next presentation on paradigms of the knowledge systems. So basically, next slide, Mori. So basically, when it comes to knowledge systems, there are two ways in which the paradigms of thinking or reasoning comes into play. So the first one is rule-based reasoning. So think of a system where if, for example, let's think of a medical system. So if certain conditions are met, then a certain result has to be given out. So that's an if and then statement. So that's what we call a rule-based reasoning. And then we have case-based reasoning. So case-based reasoning basically means prior to the knowledge system, it had a trained model, it had a trained data. So in reference to that trained data is where results are gotten from that knowledge system. So those are the two main ways in which knowledge systems work in the background. So basically that's the taxonomy of it all. Next slide. Also,
Handling uncertainty and complexity basically means if you have a knowledge system, you come across sometimes where you have, should I say, hallucinations. So basically, those knowledge systems require a dynamic way of handling ambiguities because people tend to use vague language when you're putting an input or an output. So the first way is fuzzy logic systems. So basically, that means that I've used an example of hot. Water can be hot or cold, but it can also be warm. So fuzzy logic basically means it can handle um, inputs that are variable. They're not basically defined as zeros and ones. So any value in between 0 and 1 when it comes to computation. Another way is what we call a blackboard system. So this comes into play when you have things like agentic AIs. So you have a council of AIs or a council of models or systems that actually counter check each other for the input and output they're giving out. What we call the blackboard systems. Next slide. So basically, knowledge systems have various ways in which they have structured information. So there are four basic ways. The first one is logic-based systems. So they have what we call um, formal systems for precise reasoning and using symbols and rules. Um, that's the first way in which those knowledge systems present information. The other way is structured ways where knowledge is organized into clear relationships and hierarchical uh, sy- systems. So basically, that example is semantic networks, frames, and scripts. The other one is ontology based. So basically, you define abstract concepts, entities, and interrelationships within a domain. A good example of that is abstract rules. And the last way is what we call distributed uh, ways of organizing. So this is where what we largely know as large language models do. So you actually distribute your knowledge into nodes. So that's where deep learning and AI comes into play. And next slide. So the evolution of knowledge systems basically comes from the fact that we have come from the 90s where basically we have a very narrow and crafted ways of how knowledge systems used to work. This was basically compute was very limited in the 90s, so effectiveness of such systems were not good. And then we went to the second generation between the 1980s and the 1990s. So compute, that's where compute started growing, and we basically had now professional sophisticated systems, but they're not as good as they are today. During the third phase of that generation, that's where we had a hybrid system. So we are basically moving into modern compute and microchip systems. So what we know today as the genesis of LLMs, we had things like IBM Watson and other models like AlphaGo. So that was that generation. Currently, we do have what we call the cloud-based AIs and knowledge systems, where we basically have cloud or cloud systems on ground and on space. So that's where cloud providers like AWS, Azure, and GCP come into play. And the future of it is what we call AGIs. So where we combine deep learning, reasoning, and a good example for that is Google current project on DeepMind, Google DeepMind. So here, basically, it's a fusion of DeepMind where we basically train knowledge systems based on patterns instead of we define knowledge from the back end from humans and basically teaching it how to currently notice patterns without actually telling it what it is. And that's where we are headed. So that's what we call symbolic reasoning. And a good example I've said is Google DeepMind. So that's the end for me. I'll be passing it to the next presenter.
So, morning, I'm Mark, and I'll be taking you through case-based reasoning, which is an expansion on slide 13, which which is pertaining on reasoning paradigms for knowledge systems. And here, the beginning is case-based reasoning, which is learning from experience. Normally, it is termed as the library method because it operates like a researcher looking through old files to solve a new problems. And it has three operational principles, which is match and adapt, where the system searches for the most similar past case and modifies it to fit the current situation. And the formula for it is that to get a new solution, the system will go back to the library and look through the old cases and apply minor fixes so that to give you a new solution. And for the third principle is continuous improvement, that the system solves more problems, it saves those solutions as new cases, meaning it literally gets smarter with every use. The functional note for this will be unlike rules, which are
Hello,
fixed.
Mark.
Yeah.
Mark,
Yes.
kindly, just an interruption. We are experiencing power
We are not getting
Mark,
you
hello.
clear. Hello.
I'm saying we have power interruption here in Korea.
Yeah.
So you just continue. If you see me getting out of network because
Oh,
of
okay.
my battery, don't worry. Just continue, finish up, and I
Yeah.
can tell the class we can end here, and
Yeah.
then we plan another time for this class. So this will be the last presentation. So Mark, just finish it up,
Yeah.
and we're here.
Perfect. So Nicole, on to the next slide. So there is also the neural networks, which are digital brains. So the core concept of this is that neural networks are inspired by the architecture of human brain neurons. Unlike expert systems, they learn through practice and pattern recognition rather than being programmed with explicit if-then rules. And for how they learn, it's like teaching a child to recognize a cat. You don't give them a list of descriptions about a cat over and over again. You just show them many pictures of cats until their brain recognizes the pattern and now can be able to think on its own. So the knowledge in these systems is stored as numerical weights across a network of interconnected nodes. In neural networks, the system learns from data rather than being told the logic by an expert. On to the next. So there's also genetic algorithms, which is the higher form of reasoning for knowledge systems, which is in layman's terms, digital evolution. The genetic algorithms use principles of evolutionary biology, such as selection, crossover, and mutation, to evolve solutions to optimization problems involving hundreds of variables. The three-step evolutionary process is, first of all, selection. The computer generates thousands of designs and keeps only the few that perform the best. The next one is mix, which is the crossover. The system chooses the best designs and brings them together to see if the offspring produce even if the offspring produces even better results. And for the third one, which is the mutation bit, it adds random mutations to discover new ideas or shapes that a human designer might not have considered. The perfect implementation of this will be things such as jet wings for modern airplanes and jets, more so fighter jets. Designing a perfect wing is mathematically complex. A generic algorithm can try millions of shapes, evolving the design until it finds the most fuel-efficient wing possible, which has to take into account factors like air pressure, the airflow, when we're now cutting through the air. And that is all from me. The next bit will be taken over by Abigail.
Good morning, everyone. I'll be taking you through knowledge work systems. These are specialized systems built for engineers, scientists, and other knowledge workers charged with discovering and creating new knowledge for a company. The users mainly are doctors, lawyers, engineers, and scientists, and its primary job is not just to process existing data, but to discover and create new information and knowledge for the organization. The next slide. Next slide. Major types of knowledge work systems include CAD, computer-aided design, virtual reality systems, and investment workstations. CAD automates the creation and revision of designs using high-powered graphics and computational physics. It's applied by engineers and architects to test structural integrity and performance digitally before physical prototype is built. Virtual reality systems. These interactive softwares and hardwares used to create computer-generated simulations of real-world environments. They're used by doctors for surgical simulations and by pilots for training in a risk-free immersive setting. And investment workstations are high-end desktop PCs optimized for financial professionals to access and analyze massive data in streams. They are used by hedge fund managers and stock traders. Next slide. Uh, on knowledge creation tools, we have document management systems, expert systems, and AI and machine learning tools. Document management systems, they act as institutional memory of an organization and ensure that technical reports, design documents, and historical data are stored in a centralized, searchable, retrievable formats. Expert systems are specialized software designed to encode human expertise into formula rules. An example is the MYCIN, which was developed to diagnose infectious diseases by simulating the decision making of a human specialist. In AI and machine learning, these are advanced computational tools that move beyond storage to actually discover new knowledge. An example is AlphaFold by Google DeepMind, which essentially successfully predicted the structure of nearly all proteins known to science, a task that would have taken human scientists centuries to complete. I'll be passing the, I'll let the next presenter take over, who will be Sila.
Okay, so I'll be taking through development methodology and why different. The core conflict, traditional software developments like the rigid SDLC, often they fail when applied to knowledge systems because the requirements for human wisdom are really abstract and they are difficult to define upfront. So traditional systems, they deal with well-defined predictable data processing, e.g. payroll or inventory. Then we have knowledge systems, which they deal with heuristic, uncertain, and often contradictory human expertise. The logic only becomes clear as the system is being built. The conclusion for here we have because we cannot really fully map an expert mind before we start, a linear approach is ill suited where we must move from rigid planning to iterative prototyping. The next slide. The prototyping approach. Prototyping is an iterative development technique where a small functional version of the system is built quickly to gather feedback and refine logic. We have extraction, where the knowledge engineer interviews the expert to gather the initial rules. Then we have implementation. A kernel or simple prototype is built to test the basic knowledge or logic. Then we have expert review. The expert uses the prototype and identifies where the reasoning is incorrect or incomplete. Then we have refinement. The engineer corrects the rules and expands the system based on the expert's feedback. So note the cycle repeats until the system's reasoning matches the expert performance. It is the only way to successfully extract tacit knowledge that the expert might have forgotten to mention. The next slide. The evolutionary prototyping cycle. This is the most critical development method for knowledge systems, where developers build an initial kernel and continuously refine it based on real world expert interaction. Where our first one is building the initial prototype, where we create the kernel with the most basic features and core rules.
The second is expert. The expert uses the system. The domain expert interacts with the prototype to solve test cases. Then we have expert feedback, where the expert evaluates evaluates the system reasoning and identifies errors or missing logic. Then the fourth one is refine knowledge, where the knowledge engineer modifies the rules and logic based on the feedback. The next slide. Evolutionary prototyping and feasibility. The kernel is the initial simplified version of the system that contains the most critical rules and facts. It serves as foundation for all future growth. One, we have technical feasibility. Can the knowledge actually be represented? Do we have the right inference engine and hardware? We have operation feasibility. Will the experts cooperate? Is the knowledge stable or does it change too fast to be encoded? We have economic feasibility. Does the value of the expert time saved outweigh the high cost of building and maintaining the system? Importance: if a project fails any of these tests during the prototyping phase, it should be reevaluated before further investments. The next slide. We have SDLC versus prototyping, choosing the right path. We have category number one, development philosophy, where the traditional SDLC is linear and sequential. We have evolutionary prototyping, it's iterative and recursive. The next category is requirements, fixed at start. The evolutionary is evolving. The other category is best applied to structured data for traditional, and for evolutionary is ill-structured problems, e.g. AI diagnostics. We have the other category is risk level in AI. The traditional is it's very high, rigidity trap, and we have the evolutionary is low, errors occurs early in the kernel. The next slide. I think I'm done. The next person should take over, which is Taffy.
Yes, I'm supposed to be taking you over strategic and ethics. Nicole, I can't see your screen, but never mind. So, for can you hear me? Okay. So I'll be taking you the strategic value of knowledge systems, which is where uh, thank you so much, Brian. So my name is Taffy. I'll be taking you strategic value of knowledge system, whereby it's given into where it enhance decision support and operational efficiency through AI. So, um, scenario planning system for enhanced decision support. Scenario planning systems like decision support systems and executive information systems leverage knowledge to assist management in making unstructured decisions. This is where they answer the what if questions and the scenarios by providing analyzed insights rather than just raw data. The value is it moves the organization from being a reactive to a predictive strategy. And then operational efficiency through AI. Artificial intelligence allows organization to personalize customer experiences at scale, leading to a significant competitive advantage. The example is um, organizations such as like Google and Amazon use advanced AI tools to automate complex pattern matching, whereby matching customer, like for example, matching customers to like recent interests or provide more exposure on content depending on whatever they've been clicking on. And the value is that it increases our lifetime value and operational throughput. So, next slide, please.
Can you see?
Yes.
Okay.
Um,
So the ethical and security challenges that face knowledge systems. Number one is the black box problem that my colleague Mori had previously talked about, whereby this is mainly due to accountability. Um, Many deep learning models are opaque, making it difficult to understand what is the reasoning behind specific decisions. This creates a black box effect whereby accountability is unclear. If a system makes a mistake, it is difficult to determine who is responsible or how to debug the error. Well, the second one is security of intellectual property, whereby the concept is in these systems, knowledge itself, which is now the facts, the heuristics, the algorithms that they use, is the primary compute asset. Therefore, a security breach goes beyond like simple data theft and it results in loss of proprietary expertise and corporate secrets. System integrity ends up being affected in that protecting the knowledge base from being tampered with is a critical priority. I don't know if you understand. Anyway, the third one is now the risk of bias. And whereby the concept is knowledge systems are not inherently objective. We can inherit and amplify biases present in their training data. For example, a hiring algorithm that inadvertently discriminates against specific group because of historical data used to training. And now, in conclusion, strategic strategic risk, whereby ethical transparency and asset security are essential application of some trusted knowledge-based systems. In that way, Mr. T, I was representing.
Hello? Yes, I think she's done or something.
Yes,
Yes,
it is.
Thank you so much. You people, we have a problem with power here, and it has affected a number of us here. So let's just end this class here, and then we plan next class. Next class will be on Thursday next week. There are some auditors who are coming around. Auditors from Q, from KEBS. So I will communicate clearly whether we'll manage to have it online or not. The other point is it possible for us to continue this presentation in the afternoon? It's a question. There's power outage now, but at least we've done our hours. What's your opinion? But you guys have been here. No, so let's just continue. Maybe I can just meet the afternoon group if they will be there and they have something to present. So I'll be online in the afternoon. So thank you very much. Have a good week.
You too, sir.